Look up on a dark night. That faint smudge of light left its star before you were born. It crossed an ocean of empty space just to reach you, and almost all of it slips past, unseen. Your eye is simply too small to catch it. So we built a wider eye, a bucket for starlight. Tonight we slice one open and follow a single ray of light all the way down to the back of a mirror. Start with the light itself. A star pours out energy in every direction, like ripples spreading across a still pond. By the time those ripples reach us, they have thinned across trillions of miles. What lands on your eye is a whisper. Your pupil, opened wide in the dark, is only about 7 millimeters across. That tiny window catches just a sliver of the passing wave. The rest washes by into the night. To see more, you must open a bigger window. That bigger window is the telescope's main mirror, called the primary. Think of it as a rain barrel for light. A wide barrel catches far more rain than a narrow cup. Double the width of the mirror, and you gather 4 times the light because area grows with the square of the size. A mirror the width of your hand already beats your eye many times over. More light gathered means fainter stars step out of the dark and become visible. But gathered light is useless if it stays spread out. So the primary mirror is not flat. It is gently curved, like the inside of a shallow bowl. Every ray that strikes the bowl bounces inward toward one shared meeting place. Picture a stadium full of tiny mirrors, all tilted to throw sunlight at the very same spot. That spot is the focus. There, scattered starlight is gathered back together into a single bright, concentrated image hanging in the air. The distance from the mirror to that meeting place has a name. It is the focal length. A deep, strongly curved mirror bends light hard and the rays meet close in. A shallow mirror bends gently and the rays meet far away. This length matters because it sets how large the image will be and how much we can magnify it later. For now, hold on to the picture, all that gathered starlight folded down to one glowing point of light. There is a problem. The focus forms in the middle of the tube, right where your head would block the incoming light. So we add a second, smaller mirror, tilted at an angle. It sits in the light's path and catches the beam just before it comes to a point. Then it kicks the whole cone of light sideways, out through a small hole in the side of the tube. The image moves to where your eye can finally reach it. Now the focused image arrives at the eyepiece, a small lens near your eye. The mirror did the gathering, the eyepiece does the magnifying. It works like a finely made magnifying glass held over that tiny bright image. It spreads the picture across more of your vision, so a faint disc grows into a face. Swap in a different eyepiece, and the magnification changes. The mirror stays the same, but the view zooms in close or pulls back wide. Magnification is just a ratio. Take the focal length of the big mirror and divide it by the focal length of the small eyepiece. A long mirror and a short eyepiece give high power. So if the mirror's focal length is 1000 millimeters and the eyepiece is 10, you magnify 100 times. But power has a limit. Push too far and you stretch the same light too thin and the image turns dim and blurry. Magnification only enlarges. Sharpness is a different gift. The ability to split 2 close stars into 2 clean points is called resolving power. And here, size wins again. A wider mirror sees finer detail because light behaves like a wave, and a bigger opening tames the way waves blur at the edges. This is why astronomers crave large mirrors, not only for brighter views, but for crisper ones. A small scope smears the moon's craters, a large one carves them. One thing fights you the whole time: the Earth turns. Through high magnification, that gentle spin becomes a race, and a planet drifts out of view in seconds. So the telescope rides a mount that turns slowly in the opposite direction. A small motor matches the sky's pace, one quiet turn each day. Lock onto a star, and the mount holds it still in the eyepiece, as if the whole sky had paused, just for you to look. You might ask why we bounce light instead of bending it through a lens. Lenses do work, but glass is heavy, and a large lens sags under its own weight and splits colors apart. A mirror needs only one polished surface, coated in a whisper-thin layer of aluminum. It can be made huge and held firmly from behind. That is why the giant telescopes on mountaintops all use mirrors, some as wide as a house, drinking in ancient light. So follow it once more, start to finish. Faint starlight arrives, far too weak for your eye alone. The wide primary mirror gathers it, catching far more than a pupil ever could. Its gentle curve folds every ray toward a single focus. A small angled mirror kicks that cone out the side. The eyepiece magnifies the tiny bright image by a ratio of 2 focal lengths. The mount quietly chases the turning sky. Old light finally caught and held. The next clear night, find the brightest point of light you can. Remember that it is a traveler, older than you are, crossing the dark for a very long time. And remember that a curved piece of glass can reach out and gently pull it close. Look up, then look again. This was the Cutaway.